Hello everyone, Hal here. In this video I want to walk you all through the solution to task 4 in the Q-sharp problem set. In this task we are given the problem of implementing an operation called bel, which takes as an argument a qubit array and an integer and returns a unit. The description of this operation is that based off of the integer passed to it, it will put the 2 qubits in the array into one of the 4 bel states. The second operation you need to create is called execute_4. It takes as argument an int and it returns a unit. This operation is necessary because in order to simulate our program, it is necessary to first have an entry point which makes the initial allocations of all the qubits. Okay, so to start off, we will begin by declaring our bel operation. The first argument is a qubit array, and the second argument is an integer which will indicate the bel state. And then the last thing is we return a unit, which can be thought of as a void. In order to create any of the 4 bel states, it is first necessary to put our qubits into the most basic EPR state, 5+. We already know how to do this. We've done this in earlier code. All you do is you put the first qubit into an equal superposition, and then you make a controlled NOT conditioned on the first qubit onto the second qubit. From here, all we need to do is check whether the value of state is 1, 2, or 3, and then make a handful of gate operations in order to transform our phi plus state into any of the other states. So the first condition is if state is equal to 1. If this is a situation, we are trying to make the transformation from the phi plus state into the phi minus state. In order to perform this, it is necessary to swap the phase on the 1, 1 state. Generally, to guarantee that you are swapping the phase of the amplitude on only the 1, 1 state, it is necessary to use a controlled Z operation. However, with the knowledge that our qubits are already in the phi plus state, we can use the fact that one of them being in the 1 state guarantees that the other one will be in a 1 state to save ourselves from using the costly controlled operation, and can instead just apply a Z onto either qubit 0 or 1. This will guarantee that we are in the phi minus state. The second situation is if state is equal to 2. In this situation, we are trying to transform from the phi plus state to the psi plus state. In order to do this, one of the qubits have to be swapped, so that measuring one of them gives us information that the other one is in the opposite state. In order to do this, all you have to do is swap one of the qubits in the array. Either one will work. The last situation is if state is equal to 3. In this situation, we're trying to transform the phi plus state into the psi minus state. In order to do this, we will have to use 2 separate gate operations. The first gate operation is x, which we will apply to the first qubit in the array. This will transform the phi plus state we currently have into the psi plus state. And then from here, we need to swap the phase of the amplitude where the first qubit in the array is 0 and the second qubit in the array is 1. In order to do this, we will just call a Z gate on qubit 1 in the array. Next, we need to implement operation execute_4. First, we'll start by declaring our operation. It takes as an argument an int, which we'll call state, and returns a unit. The purpose of this operation is to provide an entry point which can make the initial allocation of qubits. So the first thing we will do is make the allocation of the qubits. We will declare a qubit array of length 2, and then we will call the bel operation, passing to it the qubit array and the state. The last thing we'll do is use a function called dump machine to verify that our operation is behaving as expected. However, in order to get access to the operation, we have to open the Microsoft.quantum.diagnostics namespace. The last thing we need to do to finish execute_4 is to just reset all of our qubits. This is just good practice to do at the end of any operation. From here, we should be able to build our 2 operations. Okay, with those successfully built, we can then use magic commands to simulate our operations. and then we can vary the value of state. We could run this, and then we can manually verify that our qubits are put into each one of the Bell states. Thank you for watching, everyone. I hope this was a helpful explanation of the solution to task 4 in the Quantum Game Club Q# practice set. If you have any questions or suggestions, please feel free to leave a comment. Thank you.